All right, so we are recording. All right, so let me zoom back in on the window here. So the file that I'm going to be working on today is called mediation.dta. So again, if from stata you run, so the command to access this is, if you have a data set already showing up, you'll need to add the clear command. But if you type use http://sclight.bu.edu/harbaugh/mediation.dta, fingers crossed. I'll zoom that in so you can, just in case you make it a little larger to see there. All right. Mediation, I think I got that right.
I opened the one from last week and then just opened this one and it seems to replace it.
It did replace the other one?
Oh,
okay.
Yeah.
If not, type comma clear.
Okay. It would just show up weird, or it would be an error or something.
Yeah.
Okay.
If it didn't want to.
I assume the right variable.
Okay. So once you've done this, what you should see is the variables, and I kept the labels relatively straightforward for this. So everything is measured on a 7-point Likert type scale. A is a measure of a family's socioeconomic status. M is a measure of the academic climate of the home. And B is a number, is three items intended to capture students' long-term aspirations. In other words, do they want to go to college or do other things like that would require going to college. All right, so let me go ahead and draw the picture that we're thinking about here. I change this the layout of the slide so it's just a blank slide. Okay. All right, so we're looking at a model where we've got factor A, which we'll call SES. We've got and again, let's do this. It's A, which is SES. Then we've got, let me leave the shape browser up so I've got it there to pull stuff off. Then we've got,
4:15.
I'm calling this M, which is the academic home climate. And that includes things like, do your parents go to college? How many books do you think are at home, etc. And then last but not least, we have B, which is long-term college aspirations. We'll just say college aspirations. Okay. All right, and what we're going to do is we're looking at a mediation model. And what I want us to do is, as we go through this, we're actually going to be looking at the following hypotheses. Okay, so we're already familiar. So today's lesson is to kind of give us an idea of how we would actually go about changing models and the different things we would do. So the first hypothesis that we've looked at, the first null hypothesis, is the covariance hypothesis, which says that sigma equals sigma dependent on theta. And that's where we run the test to ask, is the data good with when we estimate the parameters from the data for a given model, does the model implied matrix look like what we think would be the population matrix for the variance and covariance? The next thing that we can then talk about are individual paths in the model, or I should more appropriately say parameters in the model. And this is, for all practical purposes, just a t-test. And I'll reiterate that as I'll bring up part of the model in there. As we're looking at the output, I'll connect it back to the model to make sure that we understand that connection. But this is pretty much the same thing that you would have done using multiple regression. When you run a regression or a multiple regression, you ask first, is the model significant? And if the model is, i.e. is enough of R squared accounted for, then you can go back and individually look at each of the coefficient slopes to decide which variable is influencing the dependent variable. Is it significant? And then if they've been standardized, can you compare them? And what we saw, if not last class, the class before, were what we call the modification indices. Okay, these are associated with the Lagrange multiplier tests. And these technically are hypothesis tests conducted using the chi-square distribution. And what I'm now going to introduce today is model changes. So when we actually change the model, we have what we call nested models, and we have non-nested models. And we're going to take a look at both of the ways that we can test here to see if we have a significant change in the model. And the part that we're not going to look at today, but which will be next time, is then group comparisons. So how do we know if one value is or isn't different from another value in a particular model? All right, so again, we've already done this one. I'll kind of put a check mark there. We've already done that one. We've pseudo done this one. I'll do a quasi check mark. And we talked about the modification indices, but I'm not sure I fully talked about the actual hypothesis measure that goes with that. So we'll talk about that one and the nested models, and we'll see that those actually go together. So I'll kind of put let's put a double. We're going to see that these ones are related, and then we will talk about the non-nested models today as well. Okay. All right, now going back to our model. So the hypothesis right now is that the working model hypothesis is that SES is probably not socioeconomic status in and of itself is probably not a good predictor of college aspirations. But SES influences the academic home culture, and the more the academic home culture, the stronger it is academic-like, the more likely someone's going to want to go to college. So if I were to add my arrows here in the model, they would look like this. And then I hate the fact that you have to reselect everything. Of course, yeah.
So you don't have to have a direct effect from SES to college aspirations to test remediation?
That's what we're going to do. We're going to put it in. We're going to see in a bit. It's going to show up, anyways. So, but I'm going to go with the initial assumption that my initial model is that I'd like to think that it's pure mediation. Okay, now that's very rare. It's very rare we ever actually have pure mediation in and of itself. But every once in a while, it does show up. But what we're going to do is essentially, this is the test, the steps we go through to convince ourselves of that. All right, so the only other part that I'm missing then is the actual number of manifest variables that we actually have here. And so we have A1. Actually, let me do this. I'll get them first. 1, 2. So A, I believe, has 4 measures. M has 4 measures. And I believe B has 3 measures. Oh, that's not what I meant to do. Okay. And again, I'll go back and draw the lines in here in a moment, but all of these now are being influenced by, so for example, this is A. These are the measurements for A. And then it's the same for all of those. Each of these then would have an error. So the only other part of the model that I really have to be careful about is A is my exogenous variable, and it's actually my only exogenous variable. M is predicted by A. M in turn is a dependent variable that also is an independent variable for B. So each of these technically should have an error term. I'll draw my errors here. So each of these would actually have an error term, and that error then is influencing. So the error in turn is also influencing each of these values. Put this over here a bit.
Why on the other side then does A not have an error?
So A, instead of having it modeled as an error term, just has its own variance.
Oh, okay.
So the when we actually make this prediction, we have a perfect prediction only because we add the error term to it. Here we just say there's a variance in this term to start. So the key is all the variance that's showing up, any value that's changing, is influenced by either A, the errors that are attached to each of these values, or the error that's in turn influencing each of these. All right, let's do a couple quick checks before we go too far. So we have how many measured variables? So 11 measured variables. Let me change the layout of this. So quick check. We have 11 measured variables. So in the matrix, so the S matrix has 11 times 12 divided by 2, or 66 distinct values. Okay, so the correlation matrix, for all those items, we have the diagonal and everything below it. That's 66 unique values, which means we have 66 pieces of information. We have, for the parameters we want to estimate, so let's think about the parameters. In this picture, so let's see, we can't see A, M, and B, okay? So what we do is, to make the model identifiable, one of the tricks that we learned very early on is we have to set one of our factor loadings to 1. It's also called an anchor loading, because you're anchoring the scale of your item to the scale of your latent variable. So each of let's do the variances for our errors first. Every variance has to be calculated. So we have 11 manifest errors. So we have 11 manifest error variances, what we would call our thetas. We have 2 zetas. Those are our endogenous errors. There we go. We have 2 endogenous error variances, or zetas. Actually, technically not zetas. Technically it would be the size, which are related to the zetas. All right. Now, for factor loadings, we have the first one's set to 1, so we have to estimate 3. Ignore 1, 3 more, that's 6. Ignore 1, 2 more, so there's 8 factor loadings. Okay, that's from the measurement model, if you wish. And then last but not least, we now have 2 paths. So we're estimating 2 paths. So we have 2, what we would call structural, my brain just froze, structural slopes. Slope coefficients. Okay. All right, so that's a total of 11. 2 and 8 is 10, so 21, 23. So our degrees of freedom then should be 66 minus 23, which equals 43.
Where did you get your factor loadings from?
So the factor loadings, the first one on every one has to be set to 1. So then there's 1, 2, 3, 4, 5, 6, because we don't count that one, 7, 8. So essentially every one of the latent constructs, I'll draw these ones in for it. So all the latent constructs have to have at least one factor loading set to 1 to be able to do the calculation. All right, so those are set to 1, and then everything else that remains I have to count. I'll estimate that loading. So again, any questions on the model? Now again, what we're going to see is we are eventually going to put a line back in here, but for now, let's go without it, and we'll see what information pops up for us.
So since you have freedom, that means that you have the ability to add in more freely estimated parameters you want, right?
Yep. Yeah. So right now there's a fair amount of room.
And then you just you use a degree of freedom, right? Each time you then add another freedom.
Yep. Every new parameter we freely estimate will give us another degree of freedom. All right, so let me label these because I think this is going to be necessary. We've got A1, A2, A3, A4, M1, M2, M3, M4. Got B1, B2, and B3. All right, so all right, at this point, let's go ahead and run the data. I think all right, so to set this up, let me scroll down a little bit here. All right, is that good enough to see? Okay. All right, so let me scooch this up a bit so it's a little higher on the screen while I'm typing this in. So I'm going to enter so it's SEM. A affects A1 through A4.
Does it matter whether you use the variable or the label?
Not sure. Don't use the label. Yep. Okay. And let me go ahead and I'm going to get rid of these just because I don't want them on there. Okay. All right. So let me switch this up. So it's SEM. The arrow points to A1 through A4. B, the arrow points to B1 through B3. Oh wait. We just said those have to be lowercase. 3. M points to M1 through M4. 30. And A points to M, and M points to B. Now, there is a model drawing feature as well, which we'll take advantage of eventually, but for now I'm just going to stick with the line codes.